Okay, so 4.6 is derivative graph analysis. And so you are going to interpret a derivative graph. On the AP exam, this can be a free response question and a multiple choice question. So typically they give you a graph of a derivative and then they ask questions about the derivative and the original function. So we're gonna definitely want to practice this. So you're going to use all the information that we've talked about in Unit 4, like increasing, decreasing, first derivative test, second derivative test, extrema, concavity, points of inflection. But you want to keep in mind what the rules are, what you're looking at, what you're looking for. It's super easy to get confused. So this will help strengthen your understanding and also help strengthen when you write things out that you're very clear on the words that you're using and the notation. So what I did was I went ahead and summarized all of the rules kind of that we've been given. So typically you're not given a graph of the original function. So I tried to write things in terms of if the derivative is negative, then your original function is decreasing. If your second derivative, and then these might be new, but they would have been presented before and you've seen this word. So you have to keep in mind that anytime you're looking for the word increasing, it implies you're taking a derivative and the sign is positive. So it really just depends on what they're looking for, what you're given, what words you're using, but be very, very, very specific. Never say it. Okay, so these are, once again, great justifications. You would just write these words out, okay? So you're not explaining how to do the calculus, you're stating the rule, and that's how you knew, okay? If that gives you any idea. So let's go ahead, and I'm not going to read through all of those, but I would print this out because it's going to be super helpful on your free response questions from now on. And just for you to know. So if you have any questions on these, we certainly can talk about them. So on my first one, and I'm kind of going to just jump all around, I'm asking you all of this information just in case. On a multiple choice question, they would just ask you one of these, okay? So I started out by using the graph of the original, okay? And you can see I'm going to keep the same curve, ask all the same things, except now I'm telling you that that's a derivative. So we'll compare how our answers change, even though the shape of the graph doesn't, but which graph I'm referring to is. Okay, so let's go ahead and just jump right in. All right, so if this is my original function, if I want to know if my f of x is increasing, I'm looking for the y values that I see. So I want my y values to get larger. So on each of these ends, it will keep going. And so we're going to get larger up until about right here. So I'm going to say that that's right here, and then right there, and then we're going to keep going. So we're going to increase from negative infinity. Remember, all of this is interval notation. It's just the easiest. I know you guys keep using your inequality symbols, but try to transition to interval notation. Okay, so typically we want to use the lowest x value, and then the highest x value. Remember, we're not really super concerned with brackets or parentheses, so for now, I would just use brackets on everything. Okay, so we go from negative infinity up until x equals -1. And then we're also increasing from 3 to infinity. F of x decreasing, so our y values decrease from -1 all the way to x equals 3. Our local max is at x equals, well, we have a max here at x equals -1, and we have a local min right here at 3. We're concave up. It's kind of hard to tell, but I'm going to assume it kind of changes the curvature about right here. If you said like 1.5, that would be okay. All right. So I'm just going to say it's at 1. And as long as you're close, I would give this to you on a quiz, and the interval would be close as well if this was multiple choice. So I'm going to say it is concave up from 1 to infinity. Because look at this curvature. And then we're concave down all the way from here to wherever you said your point was. So if you said 1.5, then this should also match. Okay, so that's kind of what I would look for on a quiz. So negative infinity to 1. right? Like I said, it could have been 1.5. It's really hard to tell. It could have even been over here at like 0.5. Be flexible. Our point of inflection is based on what you selected as your concave up and down intervals. So we say x equals 1 for me. All right, let's look at some signs. So the sign of the first derivative, which remember, if we're looking for the derivative and we're given the original, we kind of want to look at the tangent line slopes, because that's what a derivative means. So at x equals -2, I'm going to go right here, and we're going to kind of draw that tangent line. And so I know that that slope is positive. And it should make sense because our original function was increasing. That's the rule. If your first derivative is positive, your original y values are increasing. See how they match? The sign at -3, so here's -3. They're trying to trick you to say 0, but we know we're looking for the slope, so we're going to say it's also positive. At 4, here's 4. So that tangent line is also positive. And -3. Oh, so now we're at the second derivative. See? Okay. So second derivative is concavity. All right, and I'm going to change to, let's just do great. So at -3, all of these I said was concave down. So at -3, since it's concave down, we know our second derivative is going to be negative. At -2, same issue. At 0, it's right here. So negative, and then at -1, also negative. Okay? All right, so let's move on to what typically you won't be given the original function. I just want you to see the difference though, okay? So on example 2, they're going to tell you, and this is more typical, that this is a graph of the derivative. So keep in mind that these are tangent slope values that they have plotted. Like if we would go back up here and we would take all these tangent slopes and then plot them, like this is 0, this would be like 1/2, 1, 2, 4, 8. If we would plot these actual slope values, as our y values on the derivative, this is what they're saying we would get. Not on this curve. I'm just saying of another curve, okay? So these are actually tangent slope values that they use the original curve for. We don't have the original curve, so we can't do that. So just keep that in mind. I always like to write this for myself, honestly, and I've been teaching calculus for almost 15 years. Probably longer, but I'm trying not to count. All right, so let's look at this. So f of x increasing. So remember our rules say that if our derivative is positive, then our original function, the y values were increasing. So if I want my derivative to be positive, what I'm really looking for is above the x-axis, because I want my y values, my slope values that are plotted, to be positive. So we're looking, and sometimes I draw like a little line here, and I say increasing f, and down here I say f is decreasing. Okay, so we know we're above from -3 all the way to 3, and at 3 we have a slope of 0, so I would split mine up. So I would say -3 to +3, and then from 3 on. Okay, that's all of this is when my original function is increasing. And so my original function is decreasing when our y values are negative. So we're looking for under the x-axis. So from -∞ to -3. Okay. Local max and min. So remember, a local max and min, we need our slope to be equal to 0, because that made it a critical point. To go for a max, remember a max looked like this when we did our sign chart. So we needed our derivative to go from positive to negative. And for a min, we need it to look like this. So we need our derivative to go from negative to positive. So I know this is a possible max, and this is a possible max and min, because that's where our derivative is equal to 0. So then I need to check. I go from a negative to a positive. So negative to a positive, That's a minimum. So I'm going to say minimum at x equals -3. And then right here, my slope values, my derivative, went from positive to positive. So that was a possible max and min. It's still critical because my slope is 0, but because we don't change signs, we have no max. So I'm going to say none. Now, concave up. So concave up means that my second derivative, so we'll say concave up, it means that my second derivative is positive. If I have my first derivative, though, to get my second derivative, I want to take the tangent slopes to f prime, and we want those to be positive. Okay, notice I don't say of f prime. All right, so I'm going to draw in blue my tangent slope. So this I'm measuring for f prime. All of these slopes, well, right now we're all positive until we get to about right here. That means that f prime is equal to 0. So I know my tangent slopes to f prime, which makes it f double prime, are positive from -infinity to -1. So -infinity to -1. And then I'm also positive right here on my tangent slopes from 3 to infinity. Concave down means that my tangent slopes to f prime would be negative. So negative right here. So from -1 to 3. And so we have a point of inflection when our tangent slopes to f prime change from positive to negative or negative to positive. So that happens at -1 and 3. Notice it is the max and min of the derivative, okay? So now let's do some signs. So the sign of f prime is what this is, I'm going to say what you see for the y values, because this is the derivative. So if I go to -2, here's -2, here's my y value, and it's above the x-axis. Go to -3, it's on the x-axis, which is 0. It has no sign, so don't write that, just write 0. F prime of 4, that's above the axis. And so now we're going to do concavity, which talks about, oops, let's stop my circle right there. So because I want the second derivative, I want to find the tangent slopes to f prime. So at -3, let's make it green. We'll go right here. Well, that tangent slope is positive. -2, positive. At 0, that's negative. Okay? And so the sign of f, the original, so I want to know the original. Well, because we don't have any values, later on we will get to values after Christmas, but the y values of the original, we don't know. I can tell you what the y values are doing in terms of increasing and decreasing, but we don't have that answer, okay? So we don't know if it's 0, positive, or negative. We don't know anything about the original y values at all, okay? All right, so let's look at these answers. See how they're totally different, okay? A lot of the same numbers are used, but in a different way. All right, so we're going to try another question, and this one is kind of like a free response question. So they tell you the figure to the right, this is the graph of the derivative, and it does say f prime, and I just know it's really small. An odd function, what an odd function means, this goes way back to Sec 1, Sec 2, maybe Sec 3. I don't think I do it in Sec 2, but an even function means that it's symmetric. So I'm going to write a little note here. Even means symmetric about the y-axis. And so we had notations that said like f of x equals f of negative x, or f of negative x equals f of x with a negative in front. And so what happens is if this curve was even, I'm going to draw a rough shape. Okay, so if this was even, it means that I would have the same curve on the other direction. Okay, and so this comes into play, especially when we learn integrals. An odd function means mathematically that if we take f of negative x, and I'm probably not remembering this correctly, so I'm going to cross this out, it means that it's symmetric about the origin. And so what happens is if I take this curve, we know we have this, but if I would, and I can't do it, if I would turn my paper upside down, it would be the same shape. So it's going to follow the same pattern, but kind of reflect it going the other way. So I would go up this way because I'm turning my paper upside down, and then this way. So that's odd, okay? And I don't worry about the notations, so I'm just going to ignore this. You can Google it, but I don't think that helps anybody. You really do want to understand odd and even in terms of the graph, because that's how it's going to be used, not in terms of a function ever in calculus. This information might be used later on, okay? So for part A, sorry, I needed to review even and odd. It's not used very often. Nobody ever remembers it. As you can tell, I can't even remember the official notation, and I'm not even going to look it up because it's not that relevant. The graph is what you need to understand. So on this, I'm going to go ahead and just draw my little rough shape, okay? I'll label it later if I need to. Let's go ahead and erase this so I can have a clean slate. Okay, so for what values of f on -4 to 4, so that's why, because we want to go all the way, let's extend this. So this would be at -4, and this is at -2. From -4 to 4, does f have a relative minimum and a relative maximum? Okay, so remember, we want to know if we have a relative minimum when our derivative goes from, and this would be our justify. F prime goes from a minimum, we want to go like this, so we want to go from negative to positive, and then f prime goes from positive to negative. Those are our justifications. So let's look at our graph. So let's see, we go from, this is f prime, so we go from a positive to a negative at x equals -2. So, all right, and then I go from f prime is negative to a positive at 0. Then we go from a positive to a negative at 2. And then we stop here, okay? So we're not going to have another one. It does say the endpoints, so I actually like to include endpoints, but I do that separately because that's a different rule. So I would say at x equals, so what happens is because our derivative is positive, it means f is increasing. So if I start somewhere and then I start increasing up, that means that that's going to be a local min at the endpoint. And they closed this interval on our directions, so we do want to include our endpoints. So at -4, f has a local max because I would say when x is greater than -4, closely, f prime is positive, okay? And then here, what happens is my derivative was negative, so we know that our original function was decreasing. So I would be decreasing until I stopped. So that's also going to be a minimum. So I would say at x equals 4, f has a local min because when we'll say from, how about, we'll say when, let's say on, and we're just going to go from 3 to 4. We'll actually go from 2 to 4. On 2 to 4, f prime was negative. Okay. All right. On what intervals is the graph concave up? So justify. So that means that the tangent slopes to f prime are positive. Okay. And so we're going to say where it is. So we're going to go from here to there, which is at -3. So -4 to -3. We're going to go from here, which is -1, all the way to 1. And then from here, 3 to 4. Okay. Find the equation in the tangent line. So we got y minus y1 equals mx minus x1. So they gave us the point at -1. No, they didn't. So they gave us 1, the original. So f of 1, 3. And so if I had, so here's 1 up 3. And this is going to be f. If we had the point 1, 3, and I know this is an odd function, remember it's going to be symmetric about the x-axis. I'm sorry, symmetric about the origin. So if I had 1, 3, that means I'm not going to be over here. I'm going to be the reflection down. So I'm going to be at -1, -3. Okay, so that also comes into play for our ordered pair on the original, because it tells you it's odd function up. So we've got -1, -3. So y plus 3, x plus 1, and then we need our slope. So remember, it's our slope at -1, and our slope is what's graphed. So we're going to go to -1 or go to +1, it doesn't matter. And we know that our slope is 2. So at -1, our slope is -2. And you don't have to clean this up. That's good enough for me and the AP. That's it. So go through the rules, make sure you understand. When you're doing these justifications on the free response, notice how I'm not explaining how to do the problem. I'm just stating what the rule is that told me what to look for. Okay? All right, let me know if you have questions.